I've been outside in spiders, and I just need yeah, you just go at that pace.
All right, guys. No, there's no quiz today, and since we have a lot to cover, next week I think the lab will be inverters, right? Inverters. So you need to understand what an inverter is, how to operate it. So we have to cover everything today, tomorrow, Monday. Make sure you understand how that works. Okay, and then a couple other devices, pass gates, transmission gates, Scarlet equation. Yeah, a lot to cover. No time for a quiz. Good news for you guys. It's a good time to have a nap.
Yeah, I could do it.
Okay. Oh, there might be a bonus point at the end of the class. I was thinking about that before class. For example, if I ask you guys, describe what the body effect is. You know what I mean? So it won't be a quiz. If you don't do it, you are not here today. You are not losing any points. But if you turn it in, you're getting a bonus point. You know how bonus points work? It's for example, I'm giving you guys one bonus point. It's gonna be 1 out of 0. If you see this assignment on Canvas, you'll see the points is actually 0, but I'm giving you 1 out of 0. That makes sense? Yeah. Because you have other assignments, right? For example, a quiz, you got a 19 out of 20, right? So eventually, this is not contributing to this, but it's contributing to the numerator on the top. So you are actually getting bonus points. You don't want anything here, right? You don't want to divide anything. You want anything on the numerator is helping. Okay, so if you see 0 points for the assignment, which is like bonus points or something like that, don't get confused. This is what I'm gonna give to you guys. So, all right. Remember what the body effect is, how to describe it. P-in junctions. I'll do it real quick in 2 minutes. Don't want to spend too much time on this, okay? Similar concept for PMOS. I'll just show you an NMOS example here. What's this called? P-tap. P-tap. And NMOS is attracting electrons to the formal channel. And in the future, I will also ask you to explain what a pinch-off is and why the current saturates, right? Why it saturates, okay? Keep that in mind. It's gonna be bonus points in the future. So for this one, the drains, the source, this is the well. Why is the well? Even though it's not a well. So in the terminals of the transistor from the lab yesterday, you'll see the terminal of the transistor. This is labeled as W, right? It's the well. Why is it called a well? It's a well tap. Yeah. It's basically the well. So the P plus is able to have a via and connect to metal 1, right? But this well, the P well or P sub, that's a huge well, it's the wafer itself, it's the P well, is not able to directly connect to anything. They can only connect to the metal and signals through this P plus. The P plus is heavily doped, it's more conductive. So you implant this one into the P well, you are able to have a via and metal to short it to somewhere else. So we wanna so P plus represents the P well. It's a body. It's a body. It's a body. It's a substrate. So if you consider this is a pin junction, right? Pin junction, and you never want a forward biased. So how to avoid forward biasing of the pin junction here? You ground this one. So because this is P, right? This is P. The P terminal. You ground it, so it's never getting forward biased. So this is the lowest potential of the circuit. If it's not getting forward biased, there won't be any current flowing through getting into the channel. So, or you can say there's no electrons leaking from the source to the sub or to the ground. to avoid body effect. Because if you are losing electrons, you need more VGS to turn it on because it already spent so much effort keeping a decent layer sticking to the layer of the electrons, and then this is stealing electrons from it, getting thinner. So you need a higher VGS to turn it on, which is like you are increasing VTHN. So the threshold voltage is increasing, and that's called the body effect. Okay? If you don't ground the body of the NMOS, you are getting a higher threshold voltage, which is the body effect. And that is why. Okay? Very quickly. So we also talk about the saturation, a diode connection like this. There's a body connection in the middle. So we talk about this and why this is always in saturation. Because the requirement to move this one into saturation is VDS has to be larger than VDS set, which is here. Take a look at this. I'm going to give the quiz back to you guys. Remember that? VDS set. Some of you lost points on the quiz because of this curve. And so what I expected as an answer here is maybe some of the descriptions are not super accurate, but we do need two curves for each transistor. NMOS, we need a 2. PMOS, we need a 2. So NMOS, you got a VGS, here's VTHN, VGS, IDS, and we know another one for VDS, IDS, and here's VDS set. So whenever VDS is larger than VDS set, it enters saturation region. And here's like a resistors, the linear region. And here doesn't have any currents. This is called cutoff. That's it for PMOS. Same thing. It's a VSG instead. VTHP. Threshold voltage for the PMOS, which is 0.9 volts instead of 0.8 for the NMOS. Here's idea. Here's ISD. VSD. VSD set. ISD. Cutoff. Saturation. Linear. Okay? In order to keep the transistors in the saturation region, we have to keep VDS larger than VDS set, which is this direction. So what is VDS set? VDS set is VGS minus VTHN. That is VDS set by definition. So similar to this one, so VSD set for the PMOS is VSG minus VTHP. So if we do this, VGS, because that's a gate, that's a source, that's a drain. So the voltage between G and S is called VGS, and the voltage between D and S is called VDS. So if we do a connection like this, VDS equals VGS. Since we know that VDS has to be larger than VDS set, or this is basically VGS minus VTHN, it's given, right? In order to operate in saturation region, and since VDS equals VGS, if you replace this with VDS, these are equal, and this will be permanently working because VDS is always larger than VDS minus a positive number, and that's why this configuration will always operate in the saturation region if there's nothing else being added to the top. So what if you add something to the top? So here's an example for that. Any question by far? Okay, so the second time I cover this, watch the video from Monday and also revisit the video recorded now as well. If I give you a circuit like this, it's 2 volts, 100k ohms, and a short gate to drain, and this is grounded, this IDS. A circuit like this, I will be able to tell that it's not, if you have a connection like this, it's not always in saturation. It could force it into the linear region because the resistor is too big, because the voltage is too small, and it's a limited current, so there's no enough current. If you look at this, VDS, IDS, right? And if the IDS is too small because the large resistance is burning, or it's having too much current going through it, and then it's will be able to have a lower current, so force it getting to the linear region. However, we can do calculations and see if that's the case. So how do we do a calculation for this guy? So first we need to know how do we calculate, or how do we represent the IDS in the NMOS transistor. There's an equation called a square law equation. That dominates the current flowing through the channel, and IDS for the NMOS for this example equals KPN over 2 width over length, and VGS minus VTHN square. Now we don't have too many equations in this class. It's not really math heavy. It's hands heavy actually. So this is called square law equation. So KP N equals the mobility of the electrons so that's determined by the dopant density or concentration, right? So if you dope more N-type materials, there will be more free electrons, free particles, right? And then the mobility will be higher. It's a constant, determined by the process. The oxide layer's capacitance is called COX. I think this is the unit capacitance. Make sure I'm not making any errors here. Yes. And we want to say this is COXN. So we can find all these parameters from the textbook. Dr. Baker provided us with all the parameters of these guys for the model. So this is given, right? So basically this is the constant. It's called KPN. And since sometimes the width and length, you can imagine if you have a transistor and length, we want to pick up the length as the minimum length. Since all the technologies, for example, 180, 20A, 96, all the technologies, these numbers defines the length, the minimum length of the transistor. Keep that in mind. If people tell you, hey, in the interview, 180 nanometer technology, 180 nanometers means what? It means the minimum length you can make for the transistors, for the integrated circuit design. Okay, that's the minimum length. So we're gonna keep the minimum length and then modify the width to modify the current. What about changing both at the same time? They cancel out each other. Yeah. It's a ratio, and you are increasing the dimension, the footprint of the chip, making no sense. And the goal of having smaller and smaller nodes, and smaller technology, is to let us use a smaller length. If you increase it with the width at the same time, you're wasting money, right? So I told you there's a minimum length you can make, then just shrink the length and then modify the width for different current. But usually we don't really have to modify this a lot, since the digital circuit is not really manipulating the gain and everything else as an analog circuit. So we just care about, usually we just use sometimes we do 2-to-1, sometimes we keep width and length the same for the transistors, so to keep the smallest footprint. Doesn't matter, we just care about the logic. As long as the transistor is outputting a certain logic correctly, we don't really care. So we don't care about the width and length. Sometimes we give very big width, okay? That happens for a circuit like it's called buffers. Two inverters will invert the logic twice, and you are still getting the same signal. It's not changing anything. And we put these two devices into one symbol. It's a triangle. I'm sorry, it's a triangle. Just one triangle. It's not inverted because it's the same digital signal from the input to the output. However, it is a buffering the signal here. Why? It's inverting it twice.
It slows it down, doesn't it?
It slows it down, but the key point is every inverter has a VDD and ground. Okay? So you're just having more connections to the source. So it is able to, eventually these will drive the load capacitance. Since you have more connections to the VDD and ground, so whenever you are pulling this down, discharging the cap or charging on the cap using VDD, you just have more connections to the sources. It's actually dumping and pumping out, dumping in or pumping out more current from the capacitor. It's actually increasing the driving capacity of the circuit. That's why we are buffering that, because of this. Or you can use a big device. If you increase the so this is part of the lab next week. If you increase the width of the inverter, right, and then you look at the time delay at the output when it's driving a capacitor, you'll find out it's actually faster. The time delay will be smaller if you use a bigger width of the inverter. It's something you'll observe next week. What's that?
Is that just because the higher current?
It's a higher current. It's wider. So think about that. So if you are, here's a water reservoir, like a water block, a tank, right, hung there, right. I have a little bucket and you want to fill it up with water. It's actually charging out the cap, similar to that. So if you have a wider pipe connecting to the water tank, and you can efficiently charging up that little bucket or cup easily, because you have a wider diameter of the pipe, right? Similar concept. So if you have a wider transistor, it's actually a wider diameter of the pipe. Length, right? So length, if you have a shorter length of the pipe, it's actually the water can reach that bucket quicker. Okay. So that's KP. Another parameter you need to know, sometimes if you see that from the textbook, for this part, KPN times W over L. And because the width and length is a ratio, and these are all defined by the user, so they can consider as constants as well. These are given. And so if we put all these three parameters together, and we actually have another one called beta, and it's the NMOS is a beta N. You'll see this a lot in the textbook. The beta N. So this equation can be written as just try to shorten this, beta N over 2 VGS minus VTHN squared. This is given from the process, 0.8 volts for NMOS. This is customized, right? So you put a certain amount of VGS and you plug into the equation. You have all these given. You can find out IDS. It won't be 100% accurate, but it's providing some guidance to you guys. So when I'm calculating IDS, at least it's giving you a sort of like a scale of current in the channel, right? You plug in the VGS in here, you do a minus this one, do a square, and then times this parameter, you can find out the estimate of the current running through the channel. Any questions by far? So for this example, how can we find out IDS? So definitely we know.
We know the beta.
Yeah, let's do the IDS with the square law equation first. What about that? Assume that there's a KP and it's given. So KPN in the C5, I think C5. So actually even C5, 500 nanometer technology from 40 years ago, I mean, the C5 model file I gave to you guys during the lab on Tuesday, it's not the real C5 model file. I think it's shortened by the textbook. I think because even though it's still a business secret, even though it's a 40 years technology, so you won't be able to find any disclosed information about the details. But I think these numbers are close from the textbook. So KPN is 120 microamps per V squared. That's a unit. Weird unit, right? But that makes sense if you plug it in here later. We'll be able to find out. Because the voltage is getting squared, right? So this will be eventually canceled. And the dimensions are dividing each other, they are getting canceled. So only leave you the current. So that's IDS. And IDS is this, and I think it's 10/1 for width and length. You'll see this kind of note just next to the transistor a lot across the semester. It shows it's 10/1. You don't have to worry about is 10 micron by 1 micron, or is it 10 lambda by 1 lambda? It doesn't matter. If it's a ratio, it's 10/1. And this is the only thing you care about, because that's the ratio you're using for the square equation to find out the current. And this is VGS minus VTHN, which is 0.8 volts. And you also can find out IDS by doing this. Okay? Look at the resistor. So since you already introduced the VGS, can we just keep using that? Right? So VGS, because S is grounded. So VGS is the voltage at this node. That's VGS. In that case, you have 2 volts given. VGS is a variable. You have 2 volts minus VGS. You're getting the voltage drop across this resistor. And because there's nowhere the current can flow into the gate. The gate has, remember, there's a gate oxide. DC current is not getting into the capacitor. You know what I mean? There's no connection. It's oxide. Okay, no current. No current can get into it. No DC current can get into that. So IDS, what's the current here? Huh? Current. What's the current? This is not 0. This is VGS. Hmm? This is VGS. This is 2 volts.
Yeah.
What's the current?
It's 2 minus VGS over 100K.
And that's going to be IDS because there's no current can getting into this node. So the total current from here will be the same current flowing through the channel of the transistor. So they're both IDS. And you have two equations, 2 variables, 2 equations. So the 2 variables are IDS and VGS.
Yeah.
So you can find out the answer. It's a quadratic equation, but eventually there will be 2 answers. I'm not going through all the calculations, but you can see that if you plug it in, you're getting this 60 VGS square minus 95 VGS plus 36 times 4. That's what you're getting. All right. So eventually you are getting VGS as 2 values, possibly 2 possible values to satisfy the equation. One is 0.933 volts, another one is 0.65 volts.
It would have to be the 0.932.
Yeah, it has to be this one because this one will keep it on, right? The threshold voltage is 0.8 volts. So we pick up this one and drop this one, and so the transistor will be able to turn on, and it's operating in saturation. Is that in saturation? If it's on, as long as this is on, it should be in saturation or not? It should, because this equation only works for saturation. It's interesting, right? It's interesting. I don't know how to explain that, but it's been working. So what's happening is we assume, because this only works for saturation. There's another equation to describe the current in the linear region.
Yeah.
Okay, but this is for saturation only. And we assume this guy is in saturation, okay? We assume it's in saturation. And then we use this equation to find out VGS and IDS, and eventually we get one answer can satisfy that assumption. Then we say, hey, it's gonna work. So this is gonna be the voltage, and this is gonna be the current. All right? But you do need to know that if we change this resistor to a lot bigger value, like 200K, if you do it again, if you assume it's in saturation, and eventually you won't be able to find a voltage higher than 0.8 volts. So assume it, but eventually it doesn't work, which means it's not in saturation. But we assume it works, so it's in saturation.
Does this also validate that you're actually making sure your circuit's in saturation like it's supposed to? Like the transistor's actually supposed to be in saturation?
Mm-hmm. You can verify it this way, yeah.
Yeah.
So now let's talk about another important concept here. Like I said, the PMOS transistor, NMOS transistors, they are symmetrical. You can tell from the layout. You did it in the lab. From the left to right, there's no difference. Diffusions, vias, no difference. So in that case, you can treat this as D, this as S, or vice versa. Doesn't matter, okay? So like NMOS, for example, the digital signals is only 0 and VDDs. There's no other voltages. It's either 0 or VDD. Digital voltages, 0 and 5, or 0 and 1. So for the NMOS, if I turn this guy on, the digital input I'm giving in here is going to be VDD, 5 volts. Okay? Doesn't matter which is S, which is D. Doesn't matter. Let's just assume that I'm trying to pass a 5 volts to the other side. Can we do that? Can this NMOS pass the 5 volts? Can this gate pass the 0 volt?
Well, no.
If you turn it on like 5 volts, you attract a lot of electrons over here.
Yeah.
Can you detect the 0 volts here? Yes. Why? Because the electrons is forming a channel, so it's getting shorted. You got 0 volts. There's a channel connects the two terminals. No problem. And now let's increase this voltage. From 0 volts. Keep going. No problem. Until when?
They're equal?
Hmm?
Is it when the gate voltage is equal?
Like I said, either one serves as a source or drain. It has to satisfy a VGS to be at least a VTH. So VGS has to be larger than the threshold voltage. So if this one starts going up, right? Until when? You are seeing problems.
Until 5 volts?
It's too late. Hmm? 4.2, right? It's going to be VDD minus VTHN. Because if you have VDD minus VTHN, your VGS becomes VDD minus VTHN. And this is exactly VTHN, right? So that's the threshold voltage has to be satisfied in order to keep it on. If this keep going up after this value, because this is just a 0.8 volts from 5 volts. It's like 4.2 volts, right? It's keep going up until it reaches 4.2 volts. If it keep going up to like 4.3 volts, 4.5 volts, this will be shut off. And you are not getting anything over here. So that, whatever the voltage over here, won't be able to pass through the NMOS. So that's gonna be a problem. So the conclusion here is NMOS is good at doing what?
Grounding.
Passing what?
0 volt.
Passing zeros, right? Does that make sense?
Yeah.
So it's basically going here and then keep going. This won't pass. This is 4.2 volts. What about PMOS? G. So PMOS, you want to turn it on. It's a digital signal. So you turn on the PMOS, you need a 0 here. You don't have anything else. It's either 0 or VDD. So you give a 0 to the PMOS trying to turn it on. And can you pass the 0 to the other side?
Yeah, no, because you need.
You need a VSG
Yeah.
larger than VTHP. Is it larger than VTHP?
No.
No. So 0 minus 0 is still 0. It's not larger than 0.9 volts. So what's going to happen is whenever you have 0 volts, it's not going to pass. You are not able to detect the 0 volts here. However, whenever it's larger than what, all the rest will be fine. What is that voltage?
VTHP.
VTHP. What is that voltage?
0.9 or negatives.
No, 0.9 from S to G. So when this voltage is 0.9 volts, reaches 0.9 volts, you get a VSG, which is exactly the threshold voltage. So PMOS will be on. All the rest will be able to pass. What about VDD? 5 volts.
Yeah.
Fine. Yeah, VDD. Even 0.9 can turn it on. VDD will be fine because VDD is applied to source, right?
Yeah.
You are saying, why is this not source? What about this? I treat this as a source. I'm passing signal from here to here. What's the difference? The difference is just flip the paper. Same stuff.
Yeah.
You are only looking at the difference from gate to the other terminal. Doesn't matter which is S, which is D. Eventually you are passing a signal from one side to the other side. That's it. So the conclusion is PMOS is good at passing ones
VDD.
or VDDs or VDD. Doesn't matter. Same thing. Ones or VDD. Okay. You got the point? And that's a key point why we need a complementary MOS. Why it's called CMOS, right? We have complementary MOS. One is pulling up the output to VDD, and one is pulling it down to ground. It's complementary, so we have the full logic. We're not losing any voltages. If you don't have that, like only NMOS, for example, you won't be able to do one, right? Won't be able to do one. If only PMOS can do one really well, but not 0. So we need the both. And there's a important concept, and it's the way we build an inverter. We have a PMOS on the top and NMOS at the bottom, and short the two gates. And here's the output. Here's the input. Here's the inverter. Right, V in, V out. Make sense? So that's the inverter. That's a gate. You learn this gate in logic. Inverter. Not, right? Not. Why is inverting the signal from the input? So, assuming that you had a 0 for the V in for V in. Here's V out. Okay? V in is linearly increasing from 0 on x-axis, your VL will look like. So when you have a 0, what's a VL? You got 0 here. NMOS is off. You need a VDD to turn it on. If there's 0, it will not be able to turn it on. Right? NMOS is off. Gone. But 0 will be able to turn on the PMOS because I have VDD on at the source. So the VDD, the VSG, which is 5 volts, can keep it wide open. Okay. So basically, VL is being put up to VDD when the input is 0. So you're getting a 1, right? So it's inverting it because 0 input got a 1. So you're getting a 1 here, 5 volts. When VN is 0, you're getting a 5 volts for VL. Make sense? So we'll start increasing this guy, increasing the input. Here, increasing VN. And this will start decreasing, even though it's not, ideally it's gonna do this, right? It's gonna do this. But it won't be that ideal. What's gonna happen is there will be a little small ramp here. So that's what's happening. Because when VN becomes 5 volts, the VL becomes 0, because when the 5 minus 5 is 0, the VSG for the PMOS is 0, and this is off, this is gone, right? But 5 volts will be able to turn on the NMOS because you have VGS, which is 5 volts, is a lot bigger than 0.8 volts, which is threshold voltage. So VL will be put down to ground. So 5 volts input will give you a 0 output because it's being put down to ground. And that's why your VL becomes 0 afterwards. Okay? So if I plot VN in the same plot as well, I know output is VL, but if I treat, just do this, just voltage. It's not specifically a VL or VN, just another x-axis, just voltage. Same as the one on the left, okay? So VN, when VN is increasing on the x-axis, how VN will change on the y-axis. If VN increase linearly on the x, how VN can increase on the y-axis? How to plot it? How to plot it?
It's just 1 to 1.
Yeah, like this, right?
Yeah.
So in that case, if I plot VN here as well, you're seeing a curve like this. So showing VN, this is VN, this is VL. Okay? VN is your input, it's not dropping. It's not dropping to anywhere. But it could be a digital signal. If I'm giving a linear DC sweep, you are seeing this. If I should I give it a pulse? Yeah, I can give it pulse, right? So because all the digital signals are the input of the inverter can be an output of something else. So it won't be a perfect linear voltage. It could be a pulse. Imagine that. You got a lot of things here. Inverter, a lot of things here as well, right? So at a time, you gotta increase. Digital signals are not perfect, so it's gonna be like this, right? Increase, the rising edge, and you're expecting what?
Falling edge.
Okay. So if you plot them in the same curve, it'll be this input and output. Make sense?
Yeah.
This is the same curve. If you don't look at these ones, it's basically the same curve, right? Okay. So this point is called VSP. It's a switching point. What is an ideal switching point? It's 5 volts logic. 2.5 probably. Yeah. If it's shifting to the left or right, which is fine, like 2.2, 2.4 is okay, but definitely not like 1.2. So if it's a switching point at 1.2, that means anything lower than 1.2 will be treated as logic 0. Anything higher than 1.2 will be treated as logic 1.
Yeah.
That's not good. Because 1.2 is still pretty low, like 1.3 is 1. And we're expecting 5 volts to be 1, but 1.3 is way so far away from 5. So ideally you want to design something switching at 2.5. And another quick comment here. What's the voltage, digital voltage for Arduinos? 5 volts ground. So if you are doing a serial, okay, and you have a sensor, 3.3 volts. Can you directly connect these two together?
No.
It's gonna, a lot of times it's gonna burn it. Keep in mind.
Yeah, 'cause the
Like the-
voltage will be too high.
Yeah. But sometimes you can actually directly connect them to each other under some circumstances, but not all of them. Right? So which circumstance we can directly connect them together? Which one?
I guess it's the 3.3.
Yeah. So like this, right?
Yeah.
And this is not being used. It's fine. Why? Because 3.3 volts is higher than 2.5. It's logic 1, and 0 both are zeros. They know 0 are zeros, right? No difference. But once 0.3 volts is higher than 2.5, so it's treated as logic 1. So whenever this guy is reading 0.3 volts as the 1. So it's okay. But if you know that, expect any transmission, it's transmitting signal to this 3.3 volts device, never directly connected. You need a level shifter first, right?
Yeah.
But it's not always required. If you don't have anything being sent from the Arduino to the sensor, it's gonna be fine. Make sense?
Yeah.
Maybe like a 2-volt device, they wouldn't.
There aren't 2-volt devices. I've never seen that. No. There are 1-volt devices are super low power, 1.8 volts, 1 volts. But these ones definitely you need a level shifter, right? Yeah. So how do we calculate VSP? We need to calculate VSP. So if you look at VSP, it's basically the input and output, they are crossing, and the current. So the switching point defined the current in PMOS and NMOS are equal. So we call it's a switching point when the current are equal. So then we can use the square law equation. Why the current are equal? I forgot. Like why here the current are equal? Even though there's a cross, they're crossing, but this is x. Axis is voltage.
Yeah, wouldn't you want the voltages to be equal?
Hmm?
Wouldn't you want the voltages to be equal? Like
The
switch
voltage
point?
will be equal. Yes, they are equal. They are equal. But why the current are equal? I'll find out later. I forgot. So assuming that the switching point, when this happens, the PMOS and NMOS in the inverter here, they have the same current. So using square law equations, remember beta n. Beta n is the Kp times W over L. V GS, which is NMOS. The current of NMOS equals. What?
Would it be because the resistances of the transistors are equal at that point, too? So then, since they're in
I don't think the
parallel,
resistors are equal. No, the resistors are not equal.
it wouldn't be at that point.
How do we know the resistors are equal? Time current flows
But
through
they would
the
have to be.
They have to be. Yeah,
If
they
the
should be.
voltage and the current are equal, and the resistances would have to be equal as well.
Yeah.
Just according to IR equals V.
Yeah, I think so.
Yeah.
Okay. I will figure out and let you guys know Friday. Okay.
Okay.
This one, and for the PMOS, VSG minus V. So switching point, which means is actually, so V in and VR are equal, right? VSG minus VTHP. This is not changing. And VGS is what? VGS, if you see here, x-axis, when the VN reaches VSP, right? So VN equals VSP. Because VN is VGS. So VSP is basically VGS. So we can replace this guy. What about VSG? What is the VSG? And you do a square root on both sides because we know they are positive. Both are positive numbers. Because they are both on. Because the VD, the transistors are on, so these VGS, VSG are larger than the threshold voltage. So they are both positive numbers. So you can directly do a square. Just take a square root on both sides. We're getting VDD. Okay, as there's just one variable left. So by moving things around, they're getting VSP equals yeah. So this is the conclusion. Next time on Friday, we're going to directly just use this conclusion, not going to derive everything from scratch. We'll directly use this conclusion to calculate the ratio of the width and length of the PMOS and NMOS in order to reach that 2.5 volts switching point. So the whole point here is to design the size of the transistors based on their mobility, the KP and KPP, these parameters, to make sure that it's switching at 2.5 volts, not 1.2 volts. All right, that's everything for today.